Hi everyone. Welcome to mathisfun.com. Today we're going to be going over the Moivre theorem.
So first, this is de Moivre's theorem. Same thing. It states, well, you can read it on the board, but in case you can't see it, it states that cosine of x plus I times sine of x, all of this to the power of n, is equal to cosine of nx plus I times sine of nx. And this is actually very useful when doing complex numbers with respect to the Argon diagram.
Okay, so this formula right here, the Moivre's theorem, is very important because it helps us connect complex numbers like I and trigonometry, like in an Argon diagram. So later in this video, we're going to show you how to equate the left-hand side of this equation, of this formula, to the right-hand side using proof by induction. Alright, so here we have two different forms of how we can express complex numbers. First of all, we have polar form, and then we also have Cartesian form.
So with polar form, the complex number is expressed in terms of the modulus and the argument, with the modulus being the absolute value of the complex number in terms of its real and imaginary coefficients, and with the argument being its angle from the horizontal axis, which we will explain in more detail with the help of an Argon diagram later. With the Cartesian form, it's a lot more simple. It's expressed in terms of A and B, with A being the real part and B being the imaginary part.
So you may be wondering, how do we figure out what the modulus is? And how do we figure out what the argument is? So here we have two different equations to help us do that. So for R, you can basically take the Cartesian form, plug A and B inside here. So it would be A squared plus B squared, and you take the square root of that, and that would be the modulus. And for the argument, you get the inverse tangent of B over A, and that would give you the argument. And we're going to show this to you using an Argon diagram. Hi everyone, so this is the Argon diagram where we can visualize the modulus, the argument, and the entire complex number.
So given the complex number square root of 3 over 2 plus half I, we can draw it on a complex, on an Argon diagram with the x-axis representing the real component and the y-axis representing the imaginary component. So what polar form does is it expresses this number in terms of this angle here, the angle of this line from the x-axis, and the length of the hypotenuse of this right-angled triangle. And this happens to be equal to the modulus of this number. So this can be expressed as cis pi over 6 because it has a modulus of 1 and an argument of pi over 6.
Yeah. So if you plug in, so let's say this is A, this is the real part, and this part is B, right? So if you plug this, remember the equation from last time, R equals root A squared plus B squared. You have root 3 over 2 squared, which is 3 over 4, plus 1 over 4, right? So this would be equal to 1. And as we see, the hypotenuse is length 1. And let's look at tangent inverse B over A, right? So we have B over A. So it would be 1 over 2 over root 3 over 2, which is
30 degrees
the same as, same as 1 over root 3, which is pi over 6. So there you go. Using these equations, we can figure out the Argon diagram and its modulus and argument.
So now we are going to prove this by induction. So first, we have to assume that the relationship P of n is equal to this, listing out the Moivre's theorem. Cosine x plus I sine of x, all this to the power of n is equal to cosine n of x plus I sine n of x. So right now we're assuming this is true. So for step 1, we're going to verify this relationship for n equals 1. And as you can see, well, anything to the power of 1 is itself, and 1 times x is 1, so this relationship holds true for n equals 1, as left-hand side is equal to right-hand side. Now for the second step, we're going to assume that p of n is true for all n equals k, and k being an integer. So for p of k, cosine x plus I sine x, all this to the power of k, is assumed to be true, and assumed to be equal to cosine k of x plus I sine k of x.
To continue from what Isaac said, so this is step 3, and then we assume that n equals k plus 1. So we plug k plus 1 into where n was, p of k plus 1, and then we switch out the n for k plus 1. So if you get cosine x plus I sine x to the power of k plus 1, using exponents, you know that cosine x plus I sine x to the power of k times cosine x plus I sine x is the same as what was previously said. So if we plug what was said in step 2 into this step, then we know that cosine k of x plus I sine k of x is the same thing. And here, after we expand it, we get this entire expression. And then using algebra, we know that cosine k of x, kx cosine x, and so on, is the same as what's above. And then here we can simplify it into cosine kx plus x plus I sine kx plus x. And after factoring out the x, we know that cosine k plus 1x plus I sine k plus 1x is the same as cosine x plus I sine x to the power of k plus 1. So therefore, using proof by induction, we know that this expression is the same as this expression. Okay, so that's a wrap on our video. I hope you guys learned a lot about De Moivre's theorem and how we can use it to explore relationships between complex numbers and trigonometry.
This is cool. This is mathisfun.com, and we hope to have you next time.
Signing out. Peace.